Welcome back to the deep dive. Today we are tackling what is really a relentless tension at the heart of deploying large language models: continual learning.
Right.
How do you keep an LLM current? How do you get it to adapt to new information without these massive computational costs, or, and this is the big one, without it completely erasing its foundational knowledge?
Mm-hmm.
We are diving deep into a framework called LLA, that's efficient lifelong learning for adapters. And it provides a pretty novel and mathematically grounded way out of this whole catastrophic forgetting dilemma.
That's the core issue, and it is a really difficult one. For you, our expert listener, the problem really centers on this trade-off between stability and plasticity.
It's a classic trade-off.
Exactly. We need the stability, to preserve all that hard-won knowledge and
Right.
stop what we call catastrophic forgetting. But at the same time, we absolutely require plasticity to learn new things and, crucially, to get that beneficial forward transfer where past learning actually helps with future tasks.
And when you're using methods like LoRa, these parameter-efficient methods, that sequential adaptation almost always leads to just disastrous interference.
It does. And the current ways of handling this, the current CO paradigms, they're just not feasible for any kind of serious enterprise-level deployment.
Let's talk about that. I mean, if you look at what the industry is using, you see two primary failures in the sources we've reviewed.
Yeah.
First, you have replay-based methods. And okay, they work. You're literally showing the model old data again. But they are prohibitively expensive.
The storage costs, the compute.
Right. And on top of that, you have massive hurdles around data governance, privacy,
Yeah.
which for a lot of regulated environments just means they are complete non-starters.
Precisely. And so the alternative, the non-rehearsal approach, often relies on this idea of strict orthogonality. Think of methods like OLORA.
Okay.
They try to solve the interference problem by enforcing a really hard, like a zero overlap constraint between the subspaces for different tasks.
So keeping everything completely separate.
Completely separate.
Mm.
And while it does give you stability, this inductor bias is it's way too restrictive.
Yeah.
It ends up progressively shrinking the degrees of freedom for new tasks. I mean, the model literally runs out of space to learn.
And crucially, it kills any chance of positive transfer, right? Because you're forbidding all representational overlap.
You're explicitly blocking it, yeah.
Yeah.
So ELA proposes a third way.
So we have this choice between high-cost, privacy-violating replay or this super restrictive orthogonality that just chokes off learning potential. What is the core mechanism that lets ELA thread this needle?
Oh, ELA's big contribution is this new training framework that's built on a principle they call selective subspace decorrelation.
Selective, that's the key word.
That is the key word. The mission here, fundamentally, is to replace those costly or overly restrictive methods with a theoretically justified, soft, and, like you said, selective penalty. ELA doesn't forbid all overlap. It actively manages interference by looking at the structure of past updates.
Okay, let's zoom in on the geometry of this solution then. The insight seems to be that we don't have to treat all these knowledge subspaces as enemies. We just need to police the heavy hitters.
That's a perfect way to put it. So we start with the standard LoRa setup, where
Yep.
our update for a new task key to hours, is that low-rank decomposition, delta math BFBA,
Standard stuff.
totally standard. The novelty is all in how ELA encapsulates memory. It builds this thing called a cumulative signal, math BFBA6. And it's just the aggregation, the simple summation of every prior task's low-rank update. So math BFT1, delta math BFTA.
So math BFT1 isn't just a list of old tasks. It's a dense matrix that structurally encodes which parameters have been the most active, the most critical across the entire learning history.
That's exactly right. It's the aggregate memory fingerprint of the model. And then ELA applies its alignment penalty, DLA. This penalty is the squared Frobenius norm of the element-wise Hadamard product between the current update, delta math BF1ET, and that past cumulative signal, math BFWD. So the formula is delta math BFWT. That Hadamard product, the element-wise multiplication, that seems to be the crucial geometric innovation here. Why that specific structure?
Because we're not penalizing the overall magnitude of the new learning. We are penalizing the alignment of that new learning with coordinates that previous tasks have already flagged as important.
So if a coordinate in math BFWT has a high value,
And magnitude, yeah.
that tells you it's a high energy direction that was really important for past tasks. So by multiplying the new update by that past signal, we massively inflate the loss if the model tries to change those critical coordinates.
So the important directions get locked down, which encourages the new task to, specialize somewhere else. That's the stability.
That's the soft stability component.
But if a coordinate in Math BFW 2 is low magnitude, it wasn't important before, then the penalty is tiny, and the new task is free to reuse it, and that's where you get the plasticity.
Exactly. That is the essence of selective decorrelation. And practically speaking, this is just a lightweight regularizer added to the standard loss function. You just have your normal loss plus lambda times this ELA loss.
And lambda is just the one hyperparameter you need to tune.
The only one. It balances stability and plasticity. And very importantly, because ELA only tracks this one aggregated Math BFW text matrix, the whole framework is memory and compute constant. It doesn't matter if you've trained on 5 tasks or 500.
That's huge for scalability.
It's truly scalable, and it preserves zero-shot generalization during inference.
That operational simplicity is really compelling, but the real rigor here has to come from its formal guarantees, right? The paper spends a lot of time on Proposition 1. So before we get to the empirical results, let's walk through the theory that makes this all work.
Absolutely. To make sure this isn't just a clever heuristic, the paper provides a formal analysis. It actually shows there's a closed-form solution for the optimal update, delta Math BFW stare, under this regularization. And that's what they call the anisotropic shrinkage operator.
Okay, let's drill down into the mathematics here, because this is where the elegance of ELA really comes through.
Right, so if we define $d as the unconstrained gradient, that's what the model wants to do for the current task. And EA is the accumulated energy of past updates for each coordinate, plus a tiny constant for stability.
Go.
The optimal update is given by this result. Delta Math BFW star 1 plus lambda E2AG.
Wow, okay, that formula is conceptually very powerful. It's an explicit interpolation between the desired update, $, and 0. And it's governed by how busy that coordinate has been in the past.
Precisely.
So this formula is basically giving us a provably optimal way to ignore history when we need to be flexible, but to respect history when stability is paramount.
Exactly. That denominator, the $1 plus lambda E2I part, that is the anisotropic or direction-dependent part, coordinates with large past energy, where ED dollars is high. We'll see their gradient step shrunk aggressively.
That's the stability.
That's the stability. It prevents catastrophic changes. But coordinates that were low energy have almost no shrinkage, which maintains that essential flexibility for forward transfer. That's how it controls the geometry of learning.
And the second part of the proposition gives us the practical guarantee we need, bounded interference.
Right. It formalizes the whole stability goal by proving that the inner product between this optimal update and the cumulative past weights is provably bounded.
Which is the mathematical way of saying it can't interfere too much.
The formal bound is critical. It ensures the new task is constrained in how much it can mess with those dominant past directions. It's the theoretical bedrock that confirms ELA establishes a principal balance. We move from theory directly into guaranteed stability.
Okay, moving from that rigorous theory to the actual results, this is where ELA really seems to separate itself from the pack. The validation shows it getting state-of-the-art performance while keeping that constant memory and compute footprint.
The performance metrics are, they're very telling. On a standard CL benchmark, ELA hit an overall accuracy of $79.99 with T5 large. And the conceptual victory here is stark.
What do you mean?
I mean, it achieves superior accuracy compared to stronger baselines that rely on data replay, like data and recurrent KIF.
Wait, so it's beating methods that are essentially cheating by storing and looking at old data.
It's beating the cheaters, and it's doing it with a tiny constant memory budget.
And the breakdown of the CL dynamics, the forward and backward transfer, that confirms the success of this selective control, right?
It does. ELA achieves the best backward transfer, or BWT, which means less forgetting. But it also gets the highest forward transfer, FWT, which shows it's getting that constructive knowledge reuse.
And this is the critical piece of evidence against those strict orthogonality methods.
It is. OLOR gives you great backward transfer, sure, but it actually results in negative forward transfer. Learning from past tasks actively hurts its ability to learn future tasks.
So ELA proves that by selectively allowing that reuse in the low-energy subspaces, you get a positive accelerating transfer effect. The model is building knowledge constructively.
Not just defensively. And on the efficiency front, the numbers are, they're pretty compelling for anyone thinking about long-term LLM maintenance. ELA gets up to a 35 times smaller memory footprint
35 times. The source material highlights a really staggering storage reduction. Eli cuts the storage needed for T5 large from over 30 megabytes for OLoRa down to just over 4 megabytes.
Right, and that's the difference between easily managing hundreds of tasks on cheap hardware versus needing dedicated infrastructure just for memory.
And it seems to be robust across different architectures, which is vital. It works on encoder-decoder models like T5 and also on decoder-only models like LAMA 3.1.
It does, which leads to one of the most fascinating architectural observations in the results.
Let me guess. The T5XL versus LAMA 3.1 result.
That's the one. We see the smaller T5XL model, an encoder-decoder, actually achieved a higher overall accuracy than the significantly larger LAMA 3.1 8B decoder-only model.
In the continual learning setting, specifically.
In this setting, yes. And that's a major takeaway for practitioners. It strongly suggests that for continual learning, architectural choice can be more important than just raw model scale.
So why is that?
Well, the paper attributes this to T5's inherent properties, its bidirectional attention, its cross-attention mechanisms. These features just seem to be better suited for knowledge retention and transfer compared to the, causally masked unidirectional architecture of the llama family.
So forgetting is an algorithm and architecture problem, not just a size problem.
Exactly.
We have to spend a moment on the generalization ability result, the delta GA. Because normally when you do continual learning, you focus the model on specific tasks, and its general ability on things it hasn't seen tends to go down.
That is the conventional wisdom. But ELA is the exception, and this is maybe its biggest wow factor. When they tested it on unseen diverse tasks, MMLU, GSM-8K, all the big ones, ELA uniquely improves zero-shot generalization relative to the original model.
So it gets a positive delta GA.
It yields a positive delta GA. This confirms ELA is not just a defensive mechanism, it's actually facilitating constructive lifelong adaptation. The knowledge it gets from the sequential tasks synthesizes into better overall performance on things it's never seen before.
That makes it incredibly desirable for deployment. It's not just preventing loss, it's enhancing the model. Now, let's briefly touch on the ablations because they connect these practical results right back to the theoretical framework.
They do. The optimal choice of the regularization strength, lambda, aligns perfectly with the math.
How so?
The performance peaks at moderate lambda values.
Yeah.
If lambda is too small, you basically get vanilla LoRa and you see severe forgetting. The shrinkage is too weak. If lambda is too large, you shrink all the updates too aggressively. You can't learn new tasks, and accuracy drops. You become too stable.
Sacrificing plasticity. So that moderate setting proves the existence of that optimal balance the theory predicted.
It does. And the choice of the LoRa rank, dollars, is also critical. Performance consistently peaked at a rank of 8.
Not too low, not too high.
Right. A very low rank like 2 just doesn't give the model enough capacity, enough plasticity to adapt. But a high rank like 16 gives it too much capacity and it starts to overfit to the current task, which drives you right back toward catastrophic forgetting.
So synthesizing LLA's core innovation for our expert listener, it's a principled, lightweight, and really scalable path forward for CL in these models.
It is. It's a complete, replay-free, plug-and-play solution. By explicitly modeling the structure of past updates with math BFW XPath and then applying that theoretically grounded anisotropic shrinkage operator, ELA successfully manages that high-energy interference while preserving the low-energy directions.
And the result is better performance, less forgetting, enhanced transfer, and that uniquely positive impact on general ability.
That's the whole package.
It is a remarkably comprehensive solution to a problem that's been around for a long, long time. So as a final provocative thought for you to explore as you consider applying this framework, while LA has been proven highly effective in these settings, the paper does note that its scalability to scenarios involving hundreds of tasks, or even adapting it to continual multimodal LLMs, that remains an open question for future work. The general applicability of the selective decorrelation principle across increasingly complex architectures, especially those blending different modalities, that's going to be the next frontier in lifelong learning.